Question 11. So in this question, we have 4 kilogram object here. Hung vertically from a light spring that obeys Hooke's laws. It's stretched 0.025 meters. And so if you take this out and swap it with a 1.5 kilogram block, then we try to figure out what this would be. So let's draw that out. Obviously it's going to be lighter, so it's not going to stretch as much. Just 2 kilograms, or sorry, 1.5 kilograms, right? And this is for spring. And this would be let's draw this. If the face of the block would be at equilibrium, draw it like that. And that's going to be x. We'll try to solve for it. So we need to find the spring constant. And to do that, we can look at these forces acting on the block. This right here is force spring. It says it's hanging. That means it's not accelerating. So they're just equal and opposite. And this distance, 0. That's what you call this. I'm going to call it h in this case. H equals, just so we don't have too many, the same variable twice. G, so that's going to be 4 kilograms times G. There's a 4 times 9.81. And that's going to be in kilograms for the 4 meters per second squared. We have another meter here, which is equivalent of, another way to say this would be newtons divided by meter. All right, now let's look over here. Negative k h is going to be equal to, in this case it's 1.5 g. And we want to solve for h. So 1.5 times negative 9. Hold on one sec. Yeah. Divided by negative 156. 0.009375. We could say that that is 9.37 times 10 to the power of -3, or actually, let's just represent this in centimeters. That would be better. Multiplied by 100, we get 0.9375 centimeters. That's what y is going to be equal to. All right. How much work must an external agent do to stretch the same spring 4 centimeters from its unstretched position? So yeah, instead of using the weight of the block, we're just going to use an external agent in this case. Apply force, spring, and we could look at it this way, work energy theorem. So we could say a non-conservative / external force, work non-conservative, and now let's put all the initial, I mean, you could write it 2 ways, equals delta K, delta U, or sometimes I like to just jump right to this. We'd have the initial spring force, well, initial kinetic energy, initial spring force, initial height, initially it's just going to be hanging in equilibrium. There's going to be no weight, so it's just a spring from what I understand. So, and if it's in equilibrium, there's going to be no spring force because x would be equal to 0. And it's just going to be stretched, but it's not going to be moving. So let's say there's no final kinetic energy. And so I'm going to say it moves from, this is going to be initial position, and then the final position is going to be when it's all stretched out, like so. So this is y equals 0. The final potential energy is 0 because of that, because we set that y equal to 0. So let's solve for the work that the external agent must do is going to be equal to potential energy of the spring final minus, sorry, that's UG initial. So final energy of the spring is going to be half of kx squared. We might as well just plug in. We know what k is. So 4 centimeters, 0.04 meters. So now when we go on to look at potential energy, the MGH, we plug in, I plugged in 0 for mass. The reason being, it's just a point here. This doesn't have any mass. The tip of the spring is just nothing. It's just the tiniest dot. So mass is 0 kilograms. So all this here will actually just go to 0. And so when we plug this in here, we'll get 1.26 joules.